In our last class, we discussed the geometric interpretation of h of z. And we said that just by looking at an h of z, you could determine what its magnitude response looked like. Well, it's not hard to turn it from h of z into h of e to the j omega. But you could determine this by saying it's equal to the product of the distances between the frequency you're curious about, which exists along that unit circle, and the zeros. And this is a product. That's the Greek symbol capital pi, which means product, over the distances between where omega exists around that unit circle and the poles. So that's what I stated, and let me give you a demonstration that I think will show this a whole lot better. Okay, so this is a program that I wrote. You can't really see, there's two windows to it. You can't see the second window, but you can see on the left-hand side the zeros here for a simple filter, for an m equals 2 filter, FIR filter, and it's a n of 0. It has no poles at all. This is the frequency. This is the magnitude of the DTFT over here. And we're going to evaluate this on the right side by just looking at the left. So I'm going to firstly draw some lines between where our current omega is and our zeros. And right now we see that if we evaluate our DTFT at this omega equals 0 point, it's equal to this distance times this distance over 1. This is unit circle, so you actually know from trig that this is the square root of 2. So it's the square root of 2 times the square root of 2, which is 2, and it's 2 units high. But watch what happens as we increase our omega a little bit. As we increase our omega, these distances change. So let's push this up to about an omega equals pi over 4. This is about 45 degrees here. And now, although this distance is getting a little bit long, the product of this distance and this distance is getting smaller because this term that's getting smaller is going to 0 faster than this term is increasing. And so the product is getting smaller. And as we increase our frequency until it's right on top of that 0, now we're multiplying a distance of 2 by 0, and we're getting 0. So it's not surprising that our DTFT at pi over 2 is 0. And then as we increase our frequency still further, we can see that the product of these distances gets bigger. And so it's not surprising that our DTFT is highest at omega equals 0 and omega equals pi. And because there's a 0 right on that unit circle, it's guaranteed to be 0 right at pi over 2. And so just by looking at the DTFT here, without any of these dots, without any of these vector lines, you can just see now that this is going to be a band stop of pi over 2. It's not only true for these zeros, but it's also true if we put a pole on here. So here's a pole, and before I click it, someone tell me how adding this pole is going to change the DTFT.
Will it increase the magnitude of the DTFT near multiples of 2 pi and 0?
Yeah, exactly. So if we click here, that's it. Now we've got, let's bring this omega down. All right, so now our DTFT is going to be the product of green divided by the product of red. And as our red approaches 0, it will be approaching dividing by 0. And so we're going to have some sort of huge high DTFT at omega equals 0. And as omega increases, the influence of that pole will matter less and less. And so now you can see you've got some sort of weird low-pass filter that also removes pi over 2 frequencies. And we can take these things off the 0 axis. And now you can see that as we approach pi over 4, we'll tend to have a maximum, and that's what we get as we approach pi over 4. This distance is so small in the denominator that we have this big surge. Anyone have any questions about that? So the way to interpret again is you look for what poles and zeros are close to the unit circle. And then if there are any poles that are close to the unit circle, that corresponding frequency is going to boost up to infinity. I mean, remember, it's a pole. It's like a pole up in that circus tent. So you've got this membrane that goes up to infinity here. If you were to put it right on that unit circle, you can't see the difference, but this actually does go up to infinity right there. And then as we take it off the unit circle, it'll tend to decrease. We don't want to do that, though, because if we have any poles outside the unit circle, our overall system is unstable. Okay, last call for questions on that.
So, sir, just for the rules of instability,
Yes.
if your pole exists
Mhm.
on the unit circle, is that unstable, or is it just if it's beyond the unit circle?
As long as all you care about are poles, you don't care about zeros, and as long as your poles are inside the unit circle and your system is causal, which is the only types we've talked about so far, there's the only types we will talk about, then it's bibostable. And the moment you have any pole anywhere that's outside that unit circle, whether it's complex or real, it's unstable. And I haven't shown you this, but yeah, let me show you the impulse response here. Okay, so here's the impulse response. And as long as these poles are inside, you can see it tends to decay down to 0 after a while. But the moment we move the poles outside the unit circle, it goes to infinity. It becomes unstable, and these oscillations grow. If we're outside the unit circle, they do become unstable, and if we're inside the unit circle, they decay away. Any others? Is this system FIR or IAR? Finite impulse response or infinite impulse response? What do you think, Kevin?
Wouldn't it just be finite because it just goes to 0?
It sure looks like it's finite if you look at the time domain, right?
Right.
It looks like it's non-zero for at n equals 0, 1, 2, 3, 4. And then this looks almost 0, maybe it's slightly higher. This looks a little bit lower. And
it doesn't never reach 0?
It never reaches 0. And you know it
So,
never reaches 0
okay.
because of these poles.
Okay.
The only place you can have a pole in a finite impulse response is right on the right on the origin. And if we have 2 poles here, there we go. So now we've got a true finite impulse response filter. We've got something it's got 2 poles, and so it's M is 2, which means its h of n will be 3 long. It'll exist for up to n equals 2. As long as we've got these 2 zeros here, this m equals 2, it'll be a finite impulse response of length 3.